work of me and Tali Kaufman. So let's start with expander graphs. So very loosely speaking, expander graphs are sparse graphs which are strongly connected. So as you can see in this picture, for example, every vertex in this graph has only 3 edges, so it's very sparse. But every subset of vertices, has many outgoing edges, so it's very strongly connected. Now, these sort of graphs have many applications in computer science. I just mentioned 2 of them. So one is the construction of good error correcting codes by Sipser and Spearman, and also Dinur used it for to obtain a simple proof for the PCP theorem. There are many more applications, but I just mentioned these 2 because these applications also expose the limits of expander graphs, since the error correcting codes that we can get from expanders don't have the property of being locally testable. And also the PCPs constructed from expander graphs are not strong enough to yield hardness of approximation results. So as we see, there are many applications to expander graphs, but there are still some applications for which expander graphs are not good enough. So here comes the notion of high-dimensional expanders, which are stronger in a sense than expander graphs, and we hope that they might be able to achieve these applications as well. So very loosely speaking, what high-dimensional expanders? They are sparse hypergraphs, which are strongly connected. Now, when it comes to higher dimensions, the meaning of strongly connected is not so clear. There are many different suggestions for what's the right notion of expansion. I don't get into the details. Just mentioned that in recent years, there is a very active research about high-dimensional expanders. We already know that they are related to property testing questions, which is a very important field in computer science. We also know that they imply the topological overlapping property, which is a deep question in topology. So it's very interesting in many points of view. And one more thing which I find very interesting is that, in a sense, they are better than random. What I mean by that is that we know that a random graph is an expander with high probability. While we get to higher dimensions, there is no known way to achieve a high-dimensional expander with a random construction. So in a sense, it's something we cannot get with a random construction. While in graphs, it's the typical expander is a random graph. Okay, so what the objects we talk about, what are the high-dimensional version of expander graphs? So let's just focus on the 2-dimensional case. So a 2-dimensional complex is a 3 hypergraph. So we have vertices, and every edge is composed of 3 vertices, so it's basically a triangle. And then it's also closed under taking subsets. It means that if we have a triangle in our complex, then, for example, a triangle UV and W, then all of its induced edges are also in the complex. So UV, UW, and VW are also in the complex. So we have vertices, we have edges which are induced by triangles, and we have triangles. And we say that a complex is bounded degree if for every vertex the number of edges and triangles which are incident to it is bounded by some constant independent of the number of vertices in the complex. So that's the object we talk about. That's the higher dimensional version of a graph. And we focus now on a specific property of expander graphs, which is a rapid mixing of random walks. We know that a random walk on an expander graph mixes rapidly. It means that if we start from any initial vertex in the graph, and then we start moving at random between the vertices, after a few steps, we get the same, more or less the same probability to be at any vertex in the graph. Now that's the property of rapid mixing, and it has many applications in computer science. Specifically, it stands at the heart of Dinur's proof of the PCP theorem. So it's interesting to ask what's the higher dimensional version of these walks. So again, we consider a high-dimensional complex, a 2-dimensional complex in this case. We have vertices, edges, and triangles in this complex. And now we have 2 notions of random walks on this complex. We have the usual random walk that moves between vertices, like we had in graphs. But now also we have a random walk that moves between edges of the complex. We start from any initial edges, then we move between edges in the complex, where we say, when do we say the two edges are neighbors? So like in graphs, we say that two vertices are neighbors if there was an edge connecting them. Now we say that two edges are connected if there is a triangle connecting them. So for example, in this picture, if we stand at this green edge, we can move to either of these red edges. So these ones are connected to it by the upper triangle, and these ones are connected to it by the lower triangle. So now we have two notions. Okay, so now we have two notions of random walks. And the main question we ask is, do we have bounded degree complexes where all of the random walks mix rapidly? So the walk on the vertices would mix rapidly, and the walk on the edges would mix rapidly. Again, if we test the random case, we get that in expanded graph it happens, but we don't achieve it in a random construction. So we need something stronger, which is the links of the complex, which we believe is the key to study high-dimensional expansion. So I'll say what the links are. So let's see, focus on this two-dimensional. It's a small piece of a complex. We have a huge complex, and then we focus just on a small part of it. So we have vertices, edges, and triangles. And the link of this red vertex is basically the graph obtained by taking all the triangles and edges which contain this vertex, and removing this vertex from all of them. So we obtain this graph, which has now vertices and edges. And that's the link of this red vertex. It's basically the local view of the vertex. And our main theorem is that if all the links of a complex are expander graphs, then the complex itself is a high-dimensional expander in the sense that all the random walks on it mix rapidly. So note that these expanding links is a local property, and it applies a global property. If all the links locally are expander graphs, then we get the whole complex. It's a global expander that all the walks on it mix rapidly. And this property is very interesting since we know there are many constructions of expanders, but only one achieves this property of that all the links are expanders, which are the Ramanujan complexes. So our conclusion is that Ramanujan complexes are high-dimensional expanders in the sense that all random walks on them mix rapidly. I just end with a few open questions. This property of that all the links are expanders is something which it seems very powerful, but we know only one construction which achieves it. So if it's interesting to understand if there are more complexes with this property that all the links locally are expanded graphs, if someone can find another construction of such a complex, then you'll get a new construction of high-dimensional expander. And we run out of time. Okay, so just two more questions, which might be interesting. That we considered all the initial probability distributions that the random walk starts from, and it seems like there are few distributions which are bad that cause the walk to mix somehow slower. So it's interesting to see if we can recognize or maybe separate these initial probability distributions, and then for all the rest of the distributions, we'll get a very much even faster mixing of random walks. And the last question is, we know that high-dimensional expanders are pretty new to the world of computer science, and there are many applications for expanded graphs. So since high-dimensional expanders are stronger in a sense than expanded graphs, we expect them to have many applications in computer science, maybe to strengthen applications that we already have from expanded graphs, or maybe achieve new applications, as I said at the beginning. So it's interesting to find more applications for high-dimensional expanders. Right. Thank you.
Questions?
Sorry if I missed it. You said there was no random construction of high-dimensional expanders. Are there any constructions at all?
Yes, the Ramanujan complexes. There are different notions of high-dimensional expanders. So for any notion, there might be different constructions, but the Ramanujan complexes, they satisfy some of the notions. For example, the notion of having rapid mixing of random walks.
Ramanujan
constructions not conjectured? Are they conjectured to be high-dimensional expanders, or are they not?
Are they known to be random complexes? Are they known to be non-expanded?
So you can test different random constructions for all the known random constructions. They are known to be not. They are not expanded. They are not even connected. Most probably, they are not even connected. But there might be other random constructions which achieve that. But for now, it's not known.